Okay. Can you all hear me okay? Okay. Let me switch to the other talk here. All right. So welcome everybody, and it's always great having everyone in Santa Cruz. My name is Clayton Strawn. I'm a graduate student here working with Joel. So I'm going to give a talk about some of the results from AGORA. I'm very lucky that I have a talk right after him, so he got to summarize how the whole project works, and I don't have to explain any of that. Some of it will still come up, but my talk is about the AGORA CGM and about convergence between codes and about what happens when there's not convergence between codes. So there's a lot of collaborators here. Many of them are in the room. So talk to any of us if you want to know more about this project. So this is the same video that Joel watched a couple times, so I'm not going to spend too much time here, but essentially the AGORA collaboration is these 8 different codes that are all asked to do the same thing, starting from the same initial conditions. And they start off very similar at, high redshift, and then they start to kind of diverge from each other a little bit, just through kind of chaotic effects, minor things that sort of build on each other until we have kind of, structurally similar things, but which have a lot of different details. This is the Cosmo Run simulation where we have shared these things. So all of these initial conditions, heating and cooling, star formation, a lot of physics is built to be the same. This is all calibrated and checked by several steps in what Jihoon insists on calling a Herculean effort by Santi. And we have the thing that's not the same is the star formation feedback. So these are calibrated. So they are supposed to be within a factor of 5 at redshift 4. But we don't tell people which, exactly what mechanisms to use. And then there's a bunch of things that are not calibrated, which are the actual science cases, right? We can analyze these things because we didn't set them up to be anything in particular, see what the differences are. So, that's the paper that's already out is paper 3. And then there's 3 papers that will all be basically dumped on the archive all at once they're all ready. So watch out for that. And then when they're all there, go ahead and look at them all. Mine is paper 6 on the CGM. So, why are we looking at the CGM for AGORA? The main reason that the CGM is interesting is because it is usually detected in metal ion spectra, which means that it depends very sensitively on a bunch of things, right? Because the amount of a metal ion that you get is basically the product of a bunch of different terms that all can be kind of calibrated or at least looked at separately. There's like a constant amount of that atom compared to metals, and then there's 3 variables here. There's the density, the metallicity, and the ion fraction. Can all depend on the feedback setup that you use, and ion fraction, of course, depends really strongly on phase, both in temperature through collisional ionization and density through photoionization. So these codes are pretty similar. They follow this, all these different systems that they use to do feedback are able to at least maintain these within a factor of 5 with each other at redshift 4 is how they were designed. And they stay that way for a pretty long time. They stay pretty converged up down to at least redshift 2, even better than they were at redshift 4. So these systems are definitely not running away from each other, at least not at that redshift. Although it does seem like as you get lower redshift, they're starting to. For example, Enzo started with very low stellar mass and is now the highest. Art started the highest and is now the lowest. They probably will keep diverging. So after redshift 1, maybe these become too far to be comparable. But at least in this range, they're pretty close to each other, which is honestly pretty good, considering how variable the different strategies are that we used. So this is the set of codes we have. We have 8 codes. The first 3, Art, Enzo, Ramses, are grid-type codes or AMR codes. The next 3 are Chenga, Gadget, and Gear, which are particle-type codes or SPH codes. And then we have 2 what's called moving mesh codes, which have like a grid, but it's not necessarily a fixed grid like it is in these types. And they have different feedback structures. So basically, here's the setup. The T basically stands for thermal feedback. Everybody has that. Supernovas create a heat bubble right near where the supernova goes off. Some of them also have kinetic feedback. That's the K, basically saying that when a supernova goes off, it shoots gas out at some velocity rather than just heating it. We also have a couple things like radiative pressure, which is where new stars basically create a pressure term right around them before the supernovas have gone off. And delayed cooling, which is where when a supernova goes off, it sets off a bunch of ionization, and it changes the cooling structure for at least a few years, 10 megayears to 5 to 10, depending on the code. all these numerical parameters are not super important for us. These are all calibrated in order to get the same stellar mass. So these are not necessarily what people always use. This is more, these are the numbers that you calibrate. These are the things that were kind of fixed by the code type. So here's one of the pictures that shows kind of how these are different from each other. This is metallicity, density, temperature, and radial velocity. So these are an edge-on view of these codes. One interesting thing that you can see, and Joel was kind of alluding to this, is that there's a difference between how much metals are getting kicked out. So you can see in each of these codes these cool inflows, especially in the temperature plot. So they're cool, they're coming in from the left, from the right, and from kind of the top right. So there's 3 streams, so sometimes it looks like they merge, so they kind of come into the galaxy as 2. And you can see also that there is this really strong biconical outflow structure. So these have, the red velocity is basically stuff getting shot out, and the blue is stuff going in. All of these are kind of coming in along the same direction. But there is some differences. Like, for example, in these grid-type codes, we see that we have a lot faster outflows that are kicking kind of more metals out, whereas in the, but they're kind of colder. They're not as hot in these, specifically the outflows. Whereas the particle codes do kind of the opposite. They have hotter outflows that are coming out, but they're not moving as fast. So they're distributing the energy a little bit differently, right? The energy is either going into kinetic energy or it's going into thermal energy, and that kind of changes the amount of metals that get kind of kicked out that far. Where Arepo and Gizmo kind of follow. Arepo looks more like a grid code. Gizmo looks more like an SPH code. And this means they have really different distributions of stuff. So this is the distribution of metals into these 5 regions that I've defined, or 4 regions. There's the galaxy gas, the ISM. There's the galaxy stars. This is metals that are locked into stars. They can no longer really be used for anything, but this is where they went. And then the CGM is orange and the IGM is green. And one thing that's really striking here is just that there's not even any consistency on which one is winning, right? Like in some cases, such as Changa, Arepo, and Gizmo, most of the metals are still inside stars. In other cases, the metals in the ISM or in the gas phase dominate, especially in gear, but this is also true in Enzo and Gadget until very low redshift. And then some of them, which especially these 2 grid codes, Art and Ramses, they actually kick most of them out into either the CGM or into the IGM. So a lot of these metals are getting out really far. The point is that these are really different, and they clearly are doing different things and sending different amounts of stuff out into the CGM. However, we do think this is probably feedback and not the code type, right, the code architecture. The reason is because if we look at the outflows versus the inflows, so the metallicity of outflows is always higher and flatter than the metallicity of inflows with distance. That's not a surprise. This is a redshift 3 and redshift 1. So, you know, that this is higher than this is not a surprise, the shapes, but they do have a significant difference in how much metals there are total. However, if you look at, let's say, the ratio of the outflows to inflows, basically, this is talking about the dynamics inside the halo. How much is gas metals being like recycled or probably entrained, as a few talks yesterday was talking about. And they stay pretty close to each other. So they have similar dynamics, similar systems are regulating the metals. What's different is just the amount that gets kicked out initially, which is basically means this is a feedback effect, probably more than a kind of code architecture effect. But whatever it is, these are pretty far from each other as far as this goes. So, you know, what can we even learn from codes that are this different? They kind of haven't converged in this thing. Can we look at the CGM kind of in the way we wanted to? And the answer is yes, if we're careful about it. So this is a sort of integrated version of the first equation I showed, the column density of a certain ion, which is sort of the observable quantity, versus the total gas in the line of sight, metallicity, and the ion fraction along the line of sight. What we're going to do is we're going to test which of these is kind of the most predictive of these variables, right? So this is a plot of the same points in each of these 3 panels by the column density of a certain ion, here oxygen 6, versus each of these as an independent variable. So these are the same points. You can see like the same green triangle and blue triangle at the top each time. They're just kind of ordered differently. And the colors are which code it is. And I drew on these diagonal lines to show a linear relationship. Basically, if they followed one of these perfectly, then that means that that variable is controlling this outcome. And you can see for oxygen 6 that there's some correlations in total mass. There's some correlations that seem to be mostly following these diagonal lines in metallicity. There's not much correlation in ion fraction. These are all sort of more or less constant between 10 to the minus 2 and 10 to the minus 1, basically. So these are mostly depending on metallicity, right? Oxygen 6 is being predicted best by metallicity among these things. And we'll see how that kind of changes with different ions. And one thing that's interesting is that means that it matters which code you're using, right? You can see little patches of the different colors here. The blue on the right-hand side is art. The brown on the left-hand side is gear. The orange is Enzo. Pink is a repo. These are all in kind of small, discrete regions. So they're filling out this space, but no one code is filling out this whole space. It's each individual code put together that kind of fills out this metallicity space. If you look at another ion, let's add neon 8 in here. So when you add in another ion to this, this one's even more strongly controlled by metallicity. You can see that the scatter is tighter. The ion fraction is even more kind of constant. Basically, every sightline gets a similar neon 8 fraction, but they have very different amounts of neon 8 just depending on which code you're using. And so what's really neat about that is that that's completely not true with the lower ions. So I'm looking at 4 kind of medium to high ions. We didn't want to go too low because we were worried about resolution, so we don't have like magnesium 2 or something. But silicon 4 and carbon 4 are much more kind of medium ions. And in that case, it seems like they are depending much more strongly on ion fraction. Metallicity is almost not predictive at all, right? The high, art has the highest metallicity. It has both really high and really low silicon 4. It's not responding to that. Carbon 4, maybe a little bit more. You can see a trend, but it's really, really weak, a lot of scatter. It depends a lot more on ion fraction. And so if you put all these together, you get this neat kind of plot where these evolve as you go from lower to higher ionization states, where the dependence on ion fraction basically starts off more or less linear, like that's the main variable controlling your outcome, column density, and then these evolve to be more and more constant as now your sightline. Here, the sightline matters, right? Which sightline you have goes through the right state, you get a lot of this ion. If it goes through the wrong state, you get nothing. Whereas here, all the sightlines are pretty good, and it really depends more on the code and the metallicity. And so, this is kind of a neat outcome of Agora because the controlled experiment nature of this is really helpful. Because if this was a suite of simulations of a bunch of different instantiations or different masses or something, we would think that this is a mass effect. We would probably find an environmental effect. But since these are all constrained, these all have the same stellar mass, it really is just showing this is some kind of actual ionization modeling effect. This is just the nature of kind of how you do collisional and photoionization using cloudy, more than it seems like a main change with code. So this has some observable consequences, such as when you look at lower ions, they have a lot more of a radial profile change, so these fall off a lot with radius. And they're all kind of aligned with each other. So here it matters a lot more where your sightline is than which code you're using. Whereas when you look at these higher ions, it matters a lot more what code you're using, and these are a lot flatter with distance, right? So it is more affected like which code and which feedback you're using when you're looking at higher ions. And the reason for that, this is kind of my last slide, this is kind of more speculative, but this is maybe a reason for why this is happening, is that this is kind of a switch from photoionization to collisional ionization. So here we have these columns are the different codes with what we're showing is the distribution of metals into density and temperature. And on the rows, we're showing the contour plots of the different ions that we're looking at. So this bottom, there's 2 peaks. There's a collisionally ionized peak on the top right and a photoionized peak on the bottom left. For the low ions, the photoionized peak somewhat overlaps with this kind of cooling flow, these cool streams that are coming in in the CGM. And when you go to these higher ions, when you go to carbon 4, this kind of less overlaps with that stream. When you go here, it's like way too low density to appear on that stream. And you go to neon 8, like the photoionized peak is basically off screen. You can't actually get photoionized neon 8 in these simulations. So we're kind of getting a change from something that depends more on density, which changes a little bit more with distance and within a phase, to something that depends on temperature, which stays pretty much fixed with phase. So that's maybe one explanation for why this is transitioning, but I think it's helpful to think about this and try to wonder if this will depend on changes in redshift or evolution with these codes and how much this is affected by just the total amount of metals that get kicked out into this region in the first place. So that's my kind of conclusion here. We have all these different feedback strategies that can converge in star formation, but they can be very divergent in sort of distribution of metals. However, we can use that. We can use the fact that these are divergent in distribution of metals to determine that maybe metallicity actually is determining some variables where ion fraction determines other ones. So that's my talk, and thank you for your attention.
Hi. When comparing the ion fractions, do you consider the radiation from extra binaries to be a serious effect, to have a serious effect?
No, these are all using basically the default Trident setup. So what this is doing is it's using Hartmann-Dow 2012 radiation everywhere. Obviously, when you're very near the galaxy, then it can have other impacts that are affecting kind of photoionization. But in this case, yeah, it's kind of constant throughout space.
Maybe it's worth including.
It's definitely worth doing, and there's some work being done by Cameron Hummels with making Trident actually kind of access that stuff so that we can get these ion fractions in a more local way. But right now, it's really like hard computationally to figure out exactly where that comes in. But thanks.
Good. So we thank Clayton again for the very nice talk.